afternoon. Do you correctly understand me? Yeah, okay, thanks. So, as you said, my name is Jan Ramon, and I will talk about scalable federated learning in a secure and privacy preserving way with applications in a number of oncological fields. So, machine learning has proven over the last 20 years to be very useful in the biomedical field, both in research domains and in daily care of patients, for example, for decision support and for early alerts. However, machine learning models, the more you want them to be precise and performant, need more and more data. And so, to the extent that they don't have enough with patients present in one hospital. And therefore, a recent line of work has been to consider federated learning. Federated learning means that you have several hospitals which collaborate together to jointly learn a statistical model. This, however, introduces a range of new challenges because of course, we don't want that anything happens with this data, as this is personal data. And so the goal is that data remains at the hospitals and that the hospitals simply exchange encrypted messages in such a way that at the end of the process, we can only extract the statistical model we have agreed to learn. Classical machine learning research in the federated domain has assumed that parties are honest but curious, meaning they follow the protocol as described and don't perform various types of attacks. But of course, in reality, we should understand that parties may also be more malicious, and therefore that we should make systems more and more secure. There is a wide range of challenges which arise when you want to do privacy-preserving federated learning. A first range of challenges is related to the algorithms. We need to make efficient federated algorithms, we make them private, and we should make them secure. At the same time, we have the challenge of having multiple hospitals. Every hospital often has its own rules. Especially in Europe, you have national rules, you have local rules, you have European rules, and only this, not taking into account any difference in patient populations, may cause a model to behave different in the different hospitals. So there is here also a statistical challenge. Thirdly, we have data collected by several providers. There are hospitals who collect data with products of Siemens, of Philips, or of other kind of providers of hospital software, and these systems are not necessarily compatible. Even if they would use the same system, the formats of data are not always the same, and therefore efforts need to be taken to make sure this data is brought in the same format. Finally, there are, of course, also a wide range of legal challenges that need to be overcome. Overlap is specifically involved in a number of research projects working on the more algorithmic and statistical challenges, while other European projects, for example, the UK project, currently try to bring together hospitals, for example, in the case of the UK project, in the field of cancer data, to align the data, bring it in the same format, and set up procedures to let data be exploited for research. So I will, in this presentation, discuss a first challenge in some detail and a few other challenges in a bit less detail. The first one is about realistic statistical privacy. So statistical privacy is an important tool to ensure that a result of machine learning approach doesn't disclose any sensitive data. In general, we make a distinction between, on the one hand, cryptographic methods, which ensure that during the execution of an algorithm, no information leaks. So these hospitals exchange encrypted messages, and we should ensure that no information is leaking. On the other hand, there is statistical privacy, which protects the output. So currently we have neural networks and other kind of large-scale models which have millions of weights. And if you have only 1,000 of patients and these models are very well fit, tightly fit to the data, it is very well possible that sensitive personal information can be extracted from the models which you learn at the end. And therefore, we need to avoid that by making, for example, the output a bit more noisy. We add a little bit of noise so that it is not possible anymore to extract any data of individuals. It is important now to set up a metric for this. So a popular metric is differential privacy, where, for example, we have epsilon differential privacy, which ensures that if you take two adjacent data sets only differing in a single instance, that the output of the algorithm, or probabilistically, the distribution over potential outputs of the algorithm cannot be distinguished by a distance more than epsilon. And so this epsilon parameter is important, and many people then ask, okay, what parameter of epsilon should we choose? And that question leads to a lot of this confusion and discussions. One potential answer is that you just should see what people do in their daily life. If you have medical researchers write a medical paper for a medical journal, and this paper shows the data set which they use, gave for a range of features, average and standard deviation of the values in the data set, then okay, for example, if you have a data set of 100 patients, a simple exercise can show that, okay, with 20 features, you easily have something like 0.5 as your value for epsilon. If your paper contains a scatter plot, then epsilon quickly becomes 10. Good. So differential privacy allows us to accurately measure what kind of privacy guarantees an algorithm provides. And it's important to have such a metric, because then you can compare the guarantees provided by different possible solutions offered by several different researchers or providers. However, there's one important problem here. On the one hand, we don't like to add much noise to our models, since if we make our decision support noisy, then okay, maybe this doesn't benefit our patients. On the other hand, we want to guarantee, make a guarantee of privacy while adding as little noise as possible, but the assumptions made by the classical differential privacy framework are very conservative. So typically, differential privacy in the classical form makes the very strong assumption that there exists an adversary which is able to know all data and data set except for one targeted individual. And then the question is, can now the output of the algorithm reveal whether the last individual was person A or person B? That's a very strong adversary because in reality, it rarely happens that somebody is so strong. In fact, if somebody has all this knowledge, then why wouldn't he know the last patient in the data set? Therefore, a typical, many people nowadays agree that the differential privacy is an overly conservative approach. Moreover, in federated learning, we combine differential privacy, protection of the output, with cryptography, which serves the protection against leaking intermediate results. These cryptographic algorithms, multi-party computation, homomorphic encryption, which was mentioned in the previous talk, all makes certain security assumptions. They often are not information theoretically secure, but they only protect against adversaries with bounded computational power, for example. Also, they often assume that a majority of the participants, in this case the majority of the hospitals, are to some extent honest. If you don't assume that, then often well, in certain situations, you can't even prove that your algorithm will correctly finish. So the conclusion then is that it doesn't make sense to, on the one hand, be very strong on the differential privacy and not at all on the cryptographic components of the algorithm. The chain is not stronger than the weakest component. And so the proposal which we made is to develop a statistical privacy notion which makes similar assumptions as the cryptographic methods used in our system. And in this case, we assume that there is an honest fraction of, a honest majority maybe, of participants in the system, or in our case, better, an honest, we assume that a certain fraction of the data is owned by honest parties. And second, we assume that we only need to provide computational security, which means security against an attacker with only bounded computational power. Good, so this assumption leads us to a situation where we assume that the adversary only knows part of the database. So the adversary knows some observed part of the database DO, and then we have a kind of operator which extends our database with unknown data, which is sampled from the population distribution. So maybe the adversary is able to see data from one hospital or from two hospitals, but not from all hospitals. And then the fact that he doesn't know the patients in these other hospitals induce some extra uncertainty about what he can observe and what not. So, in that sense, we can define what we call honest fraction differential privacy, which means that we say that an algorithm is gamma honest fraction epsilon delta differential private if if you extend a data set with a randomly sampled block of unknown patients and then add person A or person B, in that case you still can't distinguish the output of the algorithm by a distance more than epsilon. And this is a more relaxed notion which can be satisfied with a lot less of noise. For example, if we apply this to linear regression, a classical strategy to apply differential privacy to linear regression is to add noise to the statistics. So to do linear regression, you will typically compute the average of the weights, constant factor, and the covariance of the features. And on these kind of statistics, so the statistic of the covariance matrix, of the mean of the data, and a constant factor only depending on target values, we can then add an amount of noise. However, if there is a part of the data we don't know, then this already generates a certain amount of uncertainty on these three statistics on the data, and this means that we can subtract this from the noise which we need to add to achieve differential privacy. In that sense, we can make the cost to get differentially private much smaller than the cost when you use the classical model, which satisfies both requirements of regulators who want that we have a formal guarantee that algorithms are private, and the wishes of the medical researchers who, of course, want that their statistical models are very performant. Good. So that's one possible challenge on which we are working. Another challenge in this domain of federated learning concerns the communication cost. So typically when you do federated learning, you have a kind of a global model, the current model, which you try to improve using the data. That's a typical strategy when you have a neural network, for example, and you use stochastic gradient descent, the classic algorithm, for training. You look at all data and you use the existing data to move your model a little bit in the direction of a better model. So you have the global model, you send the global model to all data owners, hospitals in our case. The hospitals will compute a gradient, compute in which direction the model should move to improve, and they will send all these gradients. Well, they will not send the gradients, they will collaborate to average the gradients together, and then the averaged gradient will be added to the model. However, this means that a lot of data needs to be sent over the network. In this case, we need to send a lot of gradients. If you have a neural network and you have 1 billion of weights, for example, because you need to work with images, and typically neural networks to handle images have lots of weights, then okay, this would mean that every iteration of this algorithm, every data owner needs to send a gigabyte of, multiple gigabytes of data over the network. If you need 1,000 iterations or 10,000 iterations, you are quickly talking about terabytes or maybe even petabytes of data you would need to send around, which is not very practical. So in this sense, there is a line of research and there is some initial work on this already, which is promising and on which we are trying to improve, where we try to compress gradients. So one strategy is to compress gradients, another strategy is to try to reduce the number of iterations needed by, for example, using second-order methods where we also compute a few second-order derivatives. Of course, not too many, because this also will generate a communication cost. So compressing gradients is possible, for example, by only sending over the network the largest component of a gradient, or by doing some low-rank approximation. Another challenge on which we are working is of verifiability. We should consider that all these data owners are now working with private data. They don't disclose the data, and the user, the researcher who sees the statistical model which is then trained, cannot verify that the computations happened correctly. This opens the possibility of all kinds of attacks, of data poisoning or modeling poisoning, where parties have the opportunities to bias the result of a study in one way or another. And therefore, it is useful to try to make algorithms verifiable even if you don't disclose the data. And the solution which has been researched in the last few years, let's say, is often a solution based on either special purpose signatures or on more general purpose zero knowledge proofs. So zero knowledge proofs have the property that you can prove certain properties without disclosing any of the data. You can prove I started with the data I claimed I have, I did my computations correctly, everything is consistent, and you can prove this without disclosing any of your data. In the beginning, this was rather expensive, but currently the size of such a proof, in fact, a kind of checksum, is only logarithmic in the size and the number of computation you need to do. So if you pack a large amount of computation in one zero knowledge proof, the cost to create, send, and verify it is not that large anymore. And then a lot of current work is a matter of logistics and of further optimizing this and making it compatible with the highly optimized existing machine learning algorithms. Okay, so in conclusion, I tried to sketch a number of challenges we are encountering in the context of privacy-preserving, secure, federated machine learning, which we apply in, for example, prostate cancer in one of our projects. And I tried to show that despite the fact that there are this number of challenges, in several cases there are solutions which are quite promising, making it possible in the very near future to exploit this technology on real-world scale data. For example, we are now running this project with a kind of 3+ for hospitals. So thanks for your attention. If you have any questions, I will be happy to answer them.